All right, hello and welcome to Real Time with Redpanda, the show about real-time streaming that we're streaming in real time so you can ask us questions if you need to. This is episode 8. We've kind of got a little bit of a last-minute switch up here. We're going to be talking about materialize. We're going to be talking about timely data flow, differential data flow, a lot of interesting stuff. We're still going to have that episode. We're going to push it back a couple weeks and reschedule that, so make sure you catch up on that one. But today we're going to be talking about consumer groups and how consumer groups work in Redpanda. And to help me out here, I've got a group of great engineers as well. We've got Alex G, regular host on Real Time with Redpanda. We've also got Noah Watkins, principal engineer here at Redpanda. So Alex G, Noah, thanks for joining me today.
Thanks for having me, Alex. Just a fun fact. I met Noah on Twitter. He actually, maybe, is it on Twitter or GitHub? I don't know. It's something like that. But basically, Noah submitted a 1,000-line CMake patch to this open source project I had called Smurf. It's this like kernel bypass RPC. And then one day I see this 1,000-line patch. I was like, who is this guy? And so it turns out that we were friends on Twitter for a while. And then I called him up, and it's basically love at first sight. And Noah joined as, I think, employee number 4 or 5. So super excited to have Noah just talk about the details of the storage engine and our thread protocol model and our consumer groups. So it's exciting. Noah, anything else that you wanted to add?
I don't think so. That was a great intro. Thanks.
Awesome. Twitter and GitHub, where all the best developer relationships are made. So,
I think for C++ is also Twitter is pretty good. So I think that's where we found each other.
Yeah, cool. So thanks for having us on today. I guess, we're going to talk a lot about consumer groups today, get deep into a lot of different things, including architecture, but maybe at a high level, let's just start off with what are consumer groups in Kafka, in Redpanda? How do they work? Why do we use them? I don't know. Noah, cool. You want to start us off with that?
Sure. Yeah. So consumer groups are really part of the Kafka protocol, and Redpanda, of course, maintains Kafka compatibility. So when you have clients that are using consumer groups, there's no difference there. So that's just to set the stage, right? This isn't like a feature that's specific to Redpanda. This applies to anybody that's using Kafka. And what consumer groups are a way for consumers to deal with parallelism, right? So it's like if you have a bunch of consumers that are consuming from topics, how do they organize themselves in order to consume from a lot of partitions, right? One way would be for all of those consumers to, I don't know, like talk to each other and figure out what they're going to do. But that would mean that basically every application in the world would have to invent their own coordination protocol. So what do consumer groups do? It's a service provided by Kafka, the protocol, and as well as Redpanda, that allows these consumers to all coordinate and decide in a structured and standard way which partitions each consumer is going to consume from. So just briefly, like say you have 100 consumers and you have a topic with 1,000 partitions, these consumers can now easily connect to a group in the cluster and divvy up this work. So it'd be like, say, each consumer is going to choose 10 partitions each to consume from, and you get this data back. So that's the first thing, parallelism and coordination. The second thing is that it tracks progress, right? So if you have consumers, say you have 100 consumers, 1,000 consumers, I don't know, the mean time to failure is, something where you have like consumers failing every day, or I don't know, maybe they're buggy and they're failing all the time. But the point is that consumers need to be able to restart their progress, right? So they're consuming from a partition or multiple partitions, and they're making progress. And if they crash, where do they resume? We don't want them to have to resume from the very beginning of the partition. So consumer groups also allow, sort of like a place for consumers to store their progress. So as consumers are reading from partitions, they're periodically committing the offset progress that they've made, and if they happen to crash, they can come back and then query where they've gotten to resume. So consumer groups are about this parallelism and coordination, and also about tracking progress to deal with failures. So I think that's like sort of the high level nutshell of consumer groups in Kafka.
Yeah, let's add actually a couple more details. Alex, do you want to switch to the drawing board real quick?
Absolutely.
And for those live in the audience, remember that you can ask questions on Twitch, and we can talk about the things that are fun and interesting here. The last thing I'll mention is we're testing a new drawing app that is collaborative. So please give us feedback. Is the Keynote on iPad better for the drawings? Well, we'll try this and let's see how it goes. So remember that topics are order collections, and so on order collections. And so a topic will typically have, let's say, two. Let's say in this case, say topic foo has two partitions, and a partition is an ordered collection. And so a topic is really a named for these two partitions. And so let's say that you have, so let's actually rebrand this piece as producers. So you have two producers producing two partition, let's say partition 0 and partition 1. And so this is on the producer side. Okay, so let's talk about the concept that Noah mentioned in just basically this. Let me give you a visual representation of why this is so important. And like basically, why should this be actually part of the Kafka protocol? And therefore, like, why do people want this, right? And sort of the multiple possible universes in which we need this. So as part of this collection, well, if you're producing, let's assume that you're also interested in consuming, right? Because otherwise then you just pipe it to dev null. And so you have consumers on the other end. And let's actually start with one consumer. So say you have consumers on this end, and right now you have one consumer. And so one thread, one Python process, it doesn't really matter, right? Like one consumer will consume these two partitions in the beginning. And so it was like, okay, let me consume from partition 0, and then let me consume from partition 1. Okay, that's great. And then you're making progress. And now this application, this consumer crashes. And so the checkpointing that Noah happened is like, so what happens? So this thing crashes, and then what do you do? So let's say for simplicity, you put it on a Kubernetes pod, and then you say pod auto restart policy. And so therefore, every time this thing crashes, it'll move the compute around, but it'll know which offset it actually consumed. That's called the checkpointing. I know I was going to talk a great deal about that in the mechanics. I'm just kind of giving you a visual representation of why this is useful. Now, let's talk about the concept of parallelism. So right now, this single consumer is consuming in the union of partition 0 and partition 1, right? It's basically, and so if you have one partition that is full, then it's probably going to dominate the amount of data that is going to consume the consumer. And so at some point, the consumer is simply not going to be able to keep up. And so you're gonna want to add a new consumer. This is where the complexity starts to happen. So when the world is simple, things are very easy. But what actually happens is when you start to scale, remember that the concept of Redpanda is actually rather trivial if you have 5 things, right? So when you show up to a restaurant and you're queuing up in line and it's first in, first out order, you can actually write these things in pen and paper, or you could use your tablet. But when you're dealing with hundreds of thousands of events per second or millions of events per second, like some of our customers, then things get complicated at that particular scale. Well, it's the same thing that happens with consumer groups. So with one consumer, it's easy. Like, okay, well, you consume this state of the world, maybe you checkpoint it manually. Well, what happens is this thing can't keep up. So what do? I still want the same mental model, but I need to add a new thing. That's when sort of the notion of consumer group really kicks in. Because what it's saying is that, instead of having, let's say this, consumer 0, consumer 0, let's give this name, consumer A and consumer B. Consumer A consume from both partitions. You have consumer A consuming from partition 0, and then consumer B consuming from partition B. This is the parallelization potential that Noah talked about, right? This clearly is like it's its own thing. It's its own basically failure mode, and then you can start to make progress, and hopefully you can keep up. Now, I mentioned the last, I think, super interesting point, which is availability of your consumers. So let's say for whatever reason that you really care about the uptime of your consumer applications. Maybe you have some tight bound SLAs. As part of the consumer groups, you can have this notion of a standby consumers in a consumer groups called consumer C. Because there are no more partitions to hand out to consumers, well, consumer C is going to do nothing. But it's there on a standby such that if this thing crashes, there's a protocol built into this consumer group protocol that Noah will talk about that will basically end up and pick up where consumer B left off, right? So all of these problems of coordination, availability, parallelism, concurrency for the consuming applications, basically the things that are actually interested in processing the data, that's what consumer groups is all about. So it's very challenging to do it at the application. You could do it, but it's very challenging to do it at the application level. And now here's another like wild dimension that Noah's going to talk about, which is, okay, let's assume that you have that. In two partitions, this thing is still even imaginably easy to understand. What happens is, what if instead of two partitions, one of our customers is trying to launch 100,000 partitions and like a consumer group with 20,000 consumer groups per consumer group. So when you get to this kind of a scale, this protocol, it starts to have a non-trivial overhead. So even this coordination protocol is non-trivial and things have to change. Anyways, this is the setup. And Noah's going to start to talk about all of these issues. I'm just trying to give you the context of like, well, what is the problem that this thing is actually solving? Like, why do we have consumer groups in the first place? And why does it have to be embedded into Redpanda proper to give you the primitive so you don't have to solve these things manually? Any questions?
I mean, I love that. So, I basically want to have these stateless consumers, but there's a lot of state associated with them. But now, I because that's sort of implemented in the Kafka protocol, I create a consumer. I just do a pull while loop and let it go, and now I don't have to worry about state as much. I just worry about processing my messages.
Yeah, exactly. And this whole latency and rebound and stuff. So now I don't know if you want to. Should we start kind of diving? Why don't you give us a background? I guess like, what's the challenge then of implementing this protocol on a thread per core model and an architecture?
Let's see. Well, I mean, the challenges that exist implementing this protocol on thread per core are really no different than the challenges that exist for probably any of the other topics you've discussed on the show about thread per core, right? So clients are connecting to Redpanda and they get assigned a particular core, and that core is the core that's handling messages from that consumer. It turns out that in a thread per core model, though, we pin state to different cores. So the core that your consumer is connected to might not be the core that is actually hosting the state for this consumer group. So when that core is handling a consumer connection, there's messages that are sent over a cross-core message bus, and this message bus has a capacity, so it can, if it fills up, there may be some issues, and we can talk about what happens there and what we've done to scale some of this stuff. But really, that's the crux of it, is getting the messages from the core handling the consumer over to the core that actually has the state. Once you're on the core that has the state, we can do all kinds of super efficient batching because we don't have any locks or any contention for manipulating the state, and the throughput can be extremely high. So I think that kind of summarizes the challenges related to thread per core.
Yeah. Alex, do you want to pipe just the drone real quick so we can see if we can keep up with Noah? Okay, let me move this thing here.
I need to get myself a tablet, I think. This drawing is very effective.
Yeah, so assume that you have I'm sure everyone has seen like the meme on like basically the Linux kernel where it's like one construction worker who has a shovel and all of the other cores are like, just looking at the one person doing work. It's basically, the consumer group, in Redpanda. So assume you have core 0, core 1, 2, 3. So you have a 4-core computer. what's happening is that let's say that you have actually let's say a consumer, and then you have a bunch of partition. Or let's say a bunch of consumers, right? And so some of these consumers, let's give these numbers: consumer 0, 1, 2, 3, consumer 4. Yeah, and then let's say even consumer 5. So wait, hold on. I think I could do this. Let me do this better. Okay.
So sorry, are you saying these are all consumers in the same group, or these are distinct groups?
Yeah,
in the same group.
So,
okay.
Yeah, let's talk about this. So actually, let me make this even more challenging. Let's say that you only have 2 cores, and that'll sort of highlight the problem. This gets exacerbated the more cores that you have. But the problem is, so you have 5 consumers in one group, and so so this is a single group. Let's call this group A. So you have group A, and let's say half of them land on core 1, and then the other will land on core 0. And so what happens is that the consumers that land in core 1, it has to make one hop, right? So one cross-core communication hop from core 1 into core 0. What Noah was saying is that once you land in core 0, because we don't have, we use a third-core architecture, we could do all sorts of efficient things like, debouncing and grouping and batching and a bunch of other things like that. And so as the consumer is making progress, so if you scroll up, Alex D, on the partition, on the order partition, remember that each consumer is keeping track of like, okay, which offset, right? I consume 1, 2, 3, 4, 5, 6. I checkpoint, and then I crash. And so next time I come back up, I want to pick up from offset 6. So it's continuously checkpointing. And so part of the consumer group protocol is basically to save data into core 0 and kind of make that hop. So the challenge that Noah was highlighting is this cross-core communication. It's like, how do you debounce? How do you make sure that you protect the cores from spamming each other? And that's I think that's basically the fundamental challenge with the third-core architecture. Noah, do we want to talk about kind of what was the progression once you land into core 0 into basically the serialization format, what ended up happening with underscore consumer offsets, and some of the optimizations that we ended up doing because of a third-core architecture?
Sure. So you're talking about once we have made the cross-core hop and we're on the core that is handling that group. Is that what you're referring to? Sure. So, basically this, the model is very similar to Kafka as well. So we are going to, execute the protocol according to the spec on that core. And then at some point, we're going to reach a state where we want to checkpoint that data. We're going to do that directly down into a Raft group. I think the last stream you had Michał Maslanka on, and he discussed the transition from that raw Raft group over into a consumer group, underscore consumer groups. So that's the state. So the state that's maintained on core 0 that's updated by the consumers as they execute. So stuff like who are the members, who are the pending members, what is their offsets, all of that data gets serialized using a super efficient native format that we have, and then we put that into the Raft group, and that Raft group is distributed across the cluster and protects that data and allows us to recover if one of the brokers that is acting as the consumer group coordinator, if it crashes, we can recover very quickly on another broker, and clients will then automatically reconnect to that broker as part of the normal reconfiguration protocol and fault recovery protocol in Kafka.
Wait, so then how does a user configure Redpanda for 2 things? One, to make sure that the consumer group has enough, because so if it's a Raft group, then it has to have partitions, right? Like, what is the replication factor on that group, and how many partitions should we talk a little bit about how do they think about configuring the cluster? So like, okay, if you lose then a Redpanda broker, you don't lose the state and progress. How do we handle that failure?
I think there's there's sort of two dimensions of configuration, right? So the first dimension is how many partitions are you going to put inside of this consumer group's topic, right? So you may have, let's say as an extreme example, you have one partition in the consumer group's topic. A little background, all of consumer group coordinators, they follow around, or they have affinity for the leader of that Raft group of the partition, right? So if you have one partition, you only have one leader, you only have one consumer group coordinator location that's possible. This means that no matter how many how many consumer groups you have, they're all going to be co-located on one core in the entire cluster. So you want to choose to have lots of partitions in this topic so that you can spread the load of consumer group affinity out across all the cores in the cluster. So that's the first dimension. The second dimension is replication factor. So each of those partitions needs to be replicated. If you have one replica, you're susceptible to availability issues and data loss. But the more that you have, the more that you have protection of that data, but also the ability to recover quickly. So as soon as a node fails, a new replica is chosen. If you have 5 replicas, for example, then you have 4 choices on where you can recover to if a broker happens to fail. So those are the 2 dimensions you want to think about when you're configuring your consumer group topics.
Gotcha. So partitions help me with scaling out. Replication helps me with recovery. I have one question on just replication generally. Do Kafka consumers ever read from non-leaders, like from replicas, or are they always reading from the leader and the replicas are just there to fail more quickly?
Right. So by default, every Kafka client is going to always go through the leader. And this is generally because we want to ensure very strong consistency, right? And so if we're all funneling through the leader, that's how we ensure that. However, you're right. Like there are cases where you may want to scale out readers, and maybe they're totally fine not seeing the very last message, right? And so this reading from replica, I believe, is a KIP enhancement, and we are working on that, but it's not enabled in Redpanda yet.
And with that, you talked about consistency, and if I recall correctly, like Redpanda, maybe we're going too far off topic here, but Redpanda, I believe, like acts to all replicas by default. Is that true? So, like, would there be less of a consistency issue there with Redpanda based on its default behavior? Or am I conflating different things?
A little bit. So, yeah. Okay. Acts equals all is, the strongest level of consistency that you're going to achieve. And that's somewhat independent of whether or not you choose to read from a replica, right? So you can still have acts all, but you can have a client that has chosen explicitly to read from a replica, and they may not provide strong consistency. But again, that's not available yet in Redpanda. Okay. So everybody's getting strong consistency.
Cool. Sounds good.
Well, I think one thing to note real quick, and I do want to get to static membership because we have to talk about this cool thing that is actually an active PR right now. Okay. When internally, when we acknowledge their rights, so remember that there is basically a series of tunable parameters in the Kafka brokers. And so the tunable parameters for safety, we talked about it extensively on the Jepsen report, so I'm not going to go into too much details. Actually, in fact, there's going to be a workshop with Kyle Kingsbury coming up. So save all of these questions of consistency and availability. And Kyle does an amazing job, and it's going to be super fun. But just to go back here to consumer groups. Go ahead.
Just two quick notes on that. Number one, I just dropped a link about that Jepsen and Redpanda webinar. It's going to be Alex. It's going to be Kyle Kingsbury talking about this stuff. So check that out. You can read the Jepsen report in chat. One other thing on this chat, we've got a few people in chat, and one of them is really relevant right now, so I want to bring it up. So just noting, something following up to what we're talking about. Kafka has some design inefficiency. Replicating for durability and replicating for high availability should be different. I don't know if that's something you want to riff on about that.
Yeah. So yes, but sorry. First thing is I do need to give the context to. So when we write internally to the rec, so at some point. This thing called like the consumer group coordinator, which is now I was talking about affinity. Actually, let's go back to the drawing board so we can talk about it. Sure. Sometimes it feels.
I've got some other questions. I want to queue those up, but yeah, keep going on this too.
All right. So let's see.
Let me know where you need to go here.
Okay, let's go down below that diagram. So assume that you have, let's say you have three computers of Redpanda, and they're all talking to each other. And let's pick one to be the coordinator. So let's say, Redpanda A is the coordinator, right? Which means that the computer that is A, remember that like you have a cluster of computers. A is the coordinator for this particular consumer group. This is what I was talking about in terms of trying to understand some failure modes of consumer groups. So let's say this crashes, and now you need either B or C to pick up, like where it goes. So what's important is that we use Ax equals sol to replicate the consumer group state, so that when a consumer group acknowledges the state, the serialized byte format on disk is replicated to all of the other brokers and saved to disk. And so this is, I think,
And that's before the
some,
write goes back to the client. Is that right?
correct. That's before, exactly.
Okay.
And so it's important because then, and so this is slightly different from some other potential implementations that it may save it to like an in-memory part of the operating system and then sort of debound the flushes, in that we guarantee that if we acknowledge the write, then it actually got written and persistent to disk. And so then what's cool about this is because it's using the Raft leadership algorithm. And now I think you can talk a little bit about how do we go about basically swapping the leadership of the coordinator from, let's say, a node crashes, and then like how do we choose one? It's basically around this node affinity thing. But then the data is already on node B and C, and so we can say, okay, node B is now the new coordinator. And then it'll just read the log that was written, localhost. And then there's this protocol for making sure that all of this, let me use a different color, all of these consumers basically consume back and change their coordinator, let's say on core 52 of computer B. Does that make sense? There's a lot of dimensions here that I think are worth highlighting. But yeah, maybe now you want to talk a little bit about that, like this coordination, why it's important to persist data to disk and so
on. Yeah. So we need to persist data to disk so that we can recover.
Yeah.
That's the most important thing. And when a fault does occur, Raft itself knows how to deal with this situation. So if a node goes down, there's a timeout that happens, and Raft will elect a new leader. Now, assuming that you've configured your system so that you have enough replicas, Raft will very quickly decide on a replacement broker to act as the new coordinator for that Raft group, and it'll go ahead and replay that log like you mentioned, and that replay is very fast because it should already be almost already fully up to date. So it may just be replaying a few little bits and pieces right at the end of the log. But as soon as it does, it's going to have recovered all the state and in memory, and then it's going to announce to the cluster, hey, I'm the new leader for this Raft group. And at that moment, clients or consumers that are connecting to the cluster are going to discover the location, very instantaneously going to discover the new location of the leader and immediately start talking to the replacement replica acting as the group coordinator.
Yeah, but I guess it's unclear to me, and I also want to answer Renee's question. Renee, it's good to see you here on the Twitch channel. Before we answer Renee's question, I think it's useful to learn. I think for people in the audience, like, well, how do we actually? Why is it that? To me, I feel like the leadership coordination protocol, right? So like you have the heartbeat expires. There's a new round of voting, and then you pick a new machine. That's part of Raft. But I think what's key for people to understand is like, how did we attach that to the partition coordination? Like, why is that true? And we basically just said, we made it so. But how does the consumer group know? He's like, hey, connect to this other computer. This other computer is the new leader. How does that
Right.
work?
It's baked into the Kafka protocol. So there's really kind of like 5 key APIs, or maybe if you wanted to call it 7, but there's 5 key APIs for the core consumer group API, right? And one of those is called find coordinator. And this is an API that a client can invoke against Redpanda, and it'll say, hey, I would really like to know which broker in the cluster is acting as the coordinator for my special group. And any node in the cluster can answer this question. And so it will compute a hash of the consumer group name, and it will, then there's like a deterministic mapping from this hash across all the cores or brokers in the cluster, and it'll just return back this answer to the client, and the client will then just immediately stop what it was doing and start directing all of its attention over to a new broker.
Yeah. And so just to highlight there, it's basically what happened is we transferred the leadership, and when we answer the next API, because the computer crashed, so the consumer groups will reach out to all of the brokers one of the brokers that it has discovered, and it's like, okay, who's the leader for this partition?
Mm-hmm.
And then, because internally we know who the leader is, then we'll respond, this is the new leader for that partition. But semantically, what it means is that we've attached the leader of the partition to the consumer group coordinator. That's basically the tie. And so we get it for free. Right? Like, you can imagine multiple things. But what we said is we already have this leadership transfer mechanism. It already rebalances across the cluster. We already have this partition count and blah, 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 and replicas and all of this. So we can recover correctly, deterministically. So all we have to do is figure out a mapping between the consumer group coordinator and the partition leader. If we make them the same, then it's easy, right? Like, sort of the mental model for the person. Okay, I think that we have another question on Twitch.
The in-sync replicas is this one.
Yeah.
So
okay. Does Redpanda use mean in-sync replicas? Redpanda does not. We are a quorum system, and so this is actually explained in detail in the Jepsen report. Actually, was it Kyle when he did the Jepsen report? No, correct me if I'm wrong, right? Like a few years ago, wasn't Kyle the one that suggested changing them in in-sync replicas? It's like a change that Kyle's an original Jepsen test on Kafka that caused 2 things, dirty leadership election and in-sync replicas to be attunable. Is that how it was?
Ooh, it was a long time ago. I think that was one of the very first systems that Jepsen was testing against. I don't quite remember, but I do remember ISR having some kind of funniness in it.
Yeah.
I don't want to
So
speculate.
that's a good question to ask Kyle. Go ahead, Alex.
So just so I understand, in-sync replica is basically saying, hey, I want to have this many or if I have a partition, each one has some replicas. I don't want them to get too far behind. And at that point, if some of them do, my leader will stop accepting writes if that happens. Is that right? In basic
it'll block. So when you write, the partition leader will block until the minimum in-sync replicas have acknowledged that write to the storage subsystem. It doesn't mean that it was written to disk, by the way. I think that's a caveat that people need to understand. It means it was written to the storage subsystem. And the storage subsystem is this totally separate subsystem that has its own tunable parameters. One is like, hey, you could write it to the page cache and like it's super fast. Or you can actually durably write it to disk and have a different level of durability, right? And so I think that's when some people were thinking about durability and availability, right? Like, I think it's very detailed, and computers are really fast. And I think that we err on the side of being safe these days. It's fundamentally different if we were operating with the spinning disk, but NVMEs are so fast. So anyways, there's kind of philosophical difference here, but yeah, so that's what it means. It means that the partition leader accepts the write, then it forwards it onto. Actually, it doesn't forward it. It waits for the ISR loop on the other read replicas to poll the Kafka, because polling is like relatively efficient as opposed to a reactive system. And then when the mini replicas act back onto the partition leader, says, "Okay, I've written it to a storage subsystem," then the producer is going to say like, "Okay, here's the ACK," and so that's the difference. And we don't do that. We are a quorum system. We are a rep, so we just simply ignore those properties. I mean, I think that sort of it's very easy to reason about a system when I can give you a math proof that says, this is what it means to have 3 out of 5 replicas up and running. This is what it means to have 4 out of 5 or 1 out of 5. Like, you understand that either what it means to have unavailability or consistency, and we choose to use a relatively consistent protocol for our replication. Kind of is a rat hole. So let's pop it back here because I want to talk about a static group membership.
Yeah, sure. Let's do it. Do you need the drawing up?
Yeah, let's talk about the... So if you scroll up just a bit onto where I wrote the 100,000, yeah, there we go, the original drawing. So, all right. So there is a ton of chatter. Noah, do we have any idea how to quantify the chatter? I guess in terms of bytes or like heartbeats.
I thought we were talking about Twitter.
That's what I thought too.
Oh, no.
I don't know how to quantify it. So there's a lot of, once you get through the initial round of the protocol, and I'm sure you're gonna get into this, right? Then it's a lot of chatter for heartbeats, and so it's it's some sort of mapping like heartbeat per second times size of the message. The message size is pretty small, but it adds up quickly.
Yeah, and so assume that you have whatever, tens of thousands of consumers. This is a relatively chatty protocol, and I think what René was actually suggesting on his comment, like, oh, consumer group rebalance, is, well, when you have a really large group, it takes a while to rebalance. And so to overcome this, I don't know, is this like design limitation probably on the original design now? There is this notion of static group membership. And actually, no, you should talk about it because you're the expert here.
We should have Michal Maslanka on. He just put up a PR to add static group membership to Redpanda. So he's the expert. But basically, the issue is that when consumers are coming and going out of a consumer group, right? So it's like you have a quiescent state, a new consumer arrives, or maybe a consumer crashes and its heartbeat times out, and the consumer group kicks that member out of the group. All of these cases trigger something called group rebalance, where the group all decides to recalculate who should be consuming from which partitions, right? And when you start to get up into consumer group sizes where there's a lot of members, or even not a lot of members, but you have flaky consumers, then you spend a lot of time engaged in this rebalancing. And so what static group membership does is says, hey, you know what, we're going to pre-configure what this balancing affinity should be, which consumers are consuming from which partitions. And this means that we can forego a lot of this rebalancing, right? So it's like if a consumer leaves or gets kicked out, then there's temporarily going to be this this time when this when nobody's consuming from whatever had been assigned to that consumer that left. But if it joins again or some other new process takes its place, it's just going to take on the role of that lost consumer, and you're able to avoid some of that rebalancing overhead. So that is static group membership. The static is sort of referring to that static assignments. Yeah.
Interesting. And so is that for folks that have much larger clusters, huge consumer groups, things like that? They'll say, hey, I'll take on a little bit of that burden of, making sure my consumer comes back up and doesn't fall too far behind, but they avoid all that rebalancing that's going on there.
Yeah, I think it's important for clusters for consumer groups where you have a large number of consumers. But it's also important for situations where you have a lot of flake. We might have like a much smaller set of consumers, but they're flaky, right? And so they're leaving and going,
constantly rebalancing.
Yeah, exactly.
Yeah.
So it's
what are the timeouts there that I think are useful for people to to note. And also, can you make a comment on __ consumer offsets? Not necessarily from an API perspective, but I think that there's this misconception in the community that __ consumer offsets is like an API, and it's actually just for ecosystem compatibility with tools like LinkedIn Borrow and a bunch of other tools. But anyways, before we get into that, let's talk about like what are some of this, like why do people care about this rebalancing? Like what's the time impact? What is the latency? So let's say you have a trading application and you have to, be up and running within an SLA of, I'm making this up, like 5 seconds, right? So like what are the potential failure modes that will cause a user to violate a particular like SLA? Like why would something take long? Like what are the points in the protocol that would basically cause an infinite timeout loop, which is often kind of hard to debug?
Yeah, I mean, I guess the easiest to sort of understand is that when consumers initially join into it, or sort of like arrive at a group, right? There's a debounce period where this rebalancing step doesn't occur, right? So if you have like 50 consumers that join very quickly together, like sort of within a few seconds, then there is no rebalancing, even though like fundamentally they're sort of joining in serial. But if a 51st consumer joins like right after that debounce period, then you have this rebalancing problem, right? So there's a tuning parameter there related to debouncing that's important. And then you can have a lot of failure modes if you are in a situation where your network is a little flaky, or there's some, there's a host of things that could cause consumers to miss those
Yeah, basically it's like a tumbling window thing where like let's say you have a window of time and then something like and this will happen in production. So for everyone tuning in, this is just a failure mode of the Kafka protocol. So you have to understand this. So let's say that you have a window of time and then you sort of come in and like right at the time of intersection, you trigger another timeout or debounce effect. Then it just extends the window again and it continues to extend the window, right? So like you have to have quiescent points, basically points where the system has reached some form of stability to make progress. Otherwise, from the point of view of the coordinator, you can't make progress. Right? Like the protocol tells you, please wait this timeout, and it's like configure. Well, I'm going to make this up, like 10 milliseconds or whatever it is. So if something keeps continuing to happen, let's say at the 7th millisecond or 8th millisecond or whatever it is, like you're just going to have this thing, and you're like, this is terrible. Like, wow. You feel like Hulk is smashing your keyboard because nothing is making progress, and you're seeing all these logs. It's like, okay, well, something is broken. I don't understand what it is, and it's like there's this critical timeouts that will simply extend the point at which your system, it's like just looks like it's halted, and it's a very sad production environment. And of course, this happens when you push a bad configuration into production in a particular app. So it's like you write an app, right? And so you're a trading application, and you say like, oh, look, I need this SLA. And so you're hacking in your application, things are great. And then you happen to introduce, let's say like you have a bad packet or like a whatever, bad something or other. And it's just always, I feel like production system will always find this particular edge cases. It's kind of mind bending, the amount of like correlated failures that you have to have, but it will happen in production. And at some point you're just like, I have no idea what is going on, but everything is crashing. And it's very frustrating. And it's just part of the consumer group protocol. Like people need to understand that this debouncing period is there to save on different edge cases. But this domain is a tunable parameter that people can set, which is how long do you wait? The longer you make it, the more the fastest time that it takes to converge, because you're just like giving people a lot of slack. The problem is you're expanding your failure window. And so at some point, it's just like, I have no idea what's going on. Basically, it's rough. Do you get that right now?
Yeah, that was an excellent description of some of the nuances.
Yeah, I know we're coming up at the top of the hour pretty soon, Alex D.
Yep. So yeah, thanks for doing this. We probably have enough content to do another consumer group or something else similar at the next time. But this was great, Noah. Thanks for joining us today. Thanks for submitting that 1,000-line PR a couple of years ago, so that you met Alex and joined the team. Alex G, great to have you as always. Just want to call out again to everyone, May 25th, put it on your calendar. There's going to be a live webinar with Kyle Kingsbury, Jepsen, Alex G, talking about, the Jepsen report that went through Redpanda. I'd say go look at that report, but then also go through in that webinar. They're going to walk through a lot of that stuff. They'll have some live Q&A. So check that out. Should be an interesting thing. I thought it was super interesting to see all the stuff that came out of the Jepsen report. So anyway, Noah, Alex, thanks for being here, and thanks everyone for watching. We'll see you next time.